All right, guys, we are back for index part number 7. This, I think, is our 8th video together right now. We're going to be covering on this one inputs, outputs, and advanced features. Now, I just want to preface this with these are not supposed to be ECU specific. It's not supposed to be application specific. We're not trying to teach you how to use a software. That's not what the intended purpose is. It's more so how an engine actually functions, and then we're operating the engine at the best way to optimize each component along that engine to, you know, give you the driving experience you're after.
And what are the key features or, let's say, functions that you need to look at in order to get the stuff to work?
Right.
Yeah.
So we have our first kickoff is going to be understanding the PID as far as what is proportional integral derivative, and the closed loop operation for that. So Claudio has a really, really good way of putting it. We have similar terminology. Go ahead.
I mean, I've always found it that the easiest way to explain something, the sort of more hands-on way that you can explain something to people without too many technical terms is sort of the best way to get around this sort of thing. So first and foremost, what is PID? It is essentially the math the ECU uses in order to meet a target. You have a closed loop O2 target, a cam position target, a boost control target. This is what the ECU, these numbers or these formulas are what the ECU uses internally to say, I want 10 pounds of boost, so I have to put X amount of pulse width to the solenoid to get it to work. Or if I'm doing, let's say, O2 control, I have to look at the tailpipe sensor, I have to see where the mixture is via the sensor, and I have to go to my lookup table, and then I want to say, I have to meet that. How much injector do I need to put or take out? So the proportional, integral, and derivative essentially are, the P is normally what you would say is the effort or the amount of work the ECU needs to put into the signal or the pulse width or the control in order to get to or close to the target. So there are normally, most ECUs will have 3 variables or 3 values or 3 tables for each of these parameters. So proportional will have its own thing, integral will have its own thing, and derivative will have its own thing. So with proportional, you're giving the ECU numbers so that it can reach target. Now you may put too big a number and the effort will go over or past and overshoot. If you put too little or not enough, then the effort will never get. It won't get to the target. Now, using only the P, your target may not be reached or may overshot and then just be dancing around the target all the time. So you don't want this instability. So where the I comes in, it is a finer adjustment of the P or the effort needed to get the target. So what you can see is when you start adding the T, this target oscillation will start to either eliminate completely or eliminate slowly over time. The ideal situation is you want the overshoot or the undershoot to get to be eliminated as quick as possible. And then finally, let me just get over to the D and then you can cut it. So and then finally you have the D, which is derivative, and then essentially Ryan had a nice little variation on the term. Says the D can be the damper, or you can also call it slowing down this effort to get the target. Now, 99.9% of the time, the D can be 0. You can get away with tuning with P and I. Otherwise, if you really need to slow down this reaching of the target, then you can incorporate the D. And the D is just very small values. You don't have to use too much. Go ahead.
So not every one of these controls will need all 3. Okay, some are just integral, some are P and I, and some are 3. So just to really simplify that and make it kind of a quick and dirty, we have the effort is our P. So the effort in which it's starting off and doing its control. Now, what are we talking about with this control? So let's say a very simple thing, boost control. I want to over 50% throttle. I want to hit 12 pounds of boost. Well, it's sending out what could be a square wave. That's just a boom, jump up and hold. Now, we know that with anything in car relation and audio relation, there are harmonics to everything. So we have an airflow that's going through to a boost control or electrical device that has a delay into it. So that delay is going to create a curvature to match as close as it can to that demanded quick jump up of a target, which is now going from, let's say, 0 to 12 psi. So to get that, we have our effort, or P. Our integrals are speed in which it is able to reach that. Now, we've got that, and we have our D, which is our derivative, but also works like a damper. So we don't want to be overshooting our targets or undershooting our targets, or maybe never getting to our targets, which is why we have a delay for our closed loop controls to even be active. Ideally, we're setting up a feed forward table, which is our lookup table for the ECU that operates on open loop initially. And when that is done at the proper level, that means that ECU is able to look up certain levels to start with. And then after a given amount of time, with an error amount that's a certain large enough region, it'll start correcting based on its error. If that's not set up first, then the ECU is always chasing unknown values. So
Here, I'll throw up a little graphic so you can correlate your explanation.
yep.
There it is.
So right here in black would be overshot target. So that's the P value is too high. And then when
And
it
probably only
passes
using
over,
P.
yes. And then this integral where it's passing over is it actually could be using I because it's continuing to overshoot. The red line here is an undershoot, but I actually prefer that to the one that they're probably thinking is ideal. Um, that 0 to 1 on the screen here is kind of like what I was saying from 0 psi to 12 psi, just a random example. And what we would want is, let's say our target is 1 on this picture, closer between the red and the green lines, where it gets as close to the blue line target as possible without overshooting or without dancing around. Now, if we find that we're still getting this oscillation like the black line after hitting, we probably have too much P. If we're seeing it, now remind me, Claudio, I'm pretty sure when we have the integral cranked, we're going to see this oscillation getting closer this way in regards to our picture.
Yes, the eye makes it really quickly get
Really
spiked.
quickly oscillate.
Yeah.
So imagine this black line instead of having 1, 2, 3 humps, as if we
All
call
the
it
humps will be
E's,
bunched up.
it would be a lot of quick ones instead. So when the eye is increased in speed, that's going to be much, much faster for reactive. And if you have damping added on top of this, now everything is getting very hot. And I actually want to take a note here. Let's close it real quick. I need this
All right,
one's a very important one.
yeah, got it.
For the electronic boost control solenoids, which are still in development, in my opinion, I don't think they're polished products. They're great, but they're still not perfectly polished. If you were to run a aggressive PID system, and this goes for every mechanical device as well,
When you say
solenoids.
aggressive, you mean to get to target quickly.
Well, I'll explain. So every mechanical device has a wear in or a wear period that it's rated for, like a million cycles or whatever for any particular device will change. Now, when you crank up the PID system of a closed loop and don't have something that is a standard operating, it is now trying to over dampen after you've already overshot. it pours a lot of heat into each of these solenoids and devices. So there was an issue on a, oh geez, I know I can tell specifics, I might as well. So Rob Dom's Fuel Tech 20V way back when, I wrote him a whole like explanation with PID, and I went through and I said, here's this, and then here's the additional ones that Fuel Tech has to control this. This was not developed. It was a Turbo Smart e-wastegate that they had tried to use initially, and it was developed on Entron. It was perfectly operable on that ECU, but not so on Fuel Tech. The reason why I'm going to this in depth is because what ended up happening is that e-wastegate failed due to temperature. And because the P, I, and D values were extremely aggressive, it ran through its, let's say, 500,000 cycle time in a matter of like 3 weeks, which it should never ever do. So
Yeah,
the
so
reason,
I guess what you're saying is essentially you're taking a component, an electronic component, in fact, that has to be zapped with electricity to get it to move. You are basically, if you can slow down time, you would basically see it just working and working and working. It's like
yes,
opening and closing a door on a car a million times in about an
yep,
hour. So
yep, that's
you're
exactly what had happened.
you're
So
you're
it,
putting more mechanical effort into a device that it's rated for X amount of mechanical efforts, and then that makes its life shorten up.
yep. So on this understanding the whole PID, this is why we have feed forward tables. This is why we take the time to create these so that we don't rely on them. This is
Explain
the
what are feed forward tables. That's a good explanation.
so here, I'll actually start pulling something up on my end, but the best way to explain it is let's say that we had a table of a very simple one would be like RPM versus estimated boost pressure. So on our boost controller shut off, we're making a spring pressure of 12 psi. With that boost controller just starting to activate, which when you increase the frequency, you're going to decrease the range of its usability. So when that table starts up, let's say we have 15% duty cycle, brings us about 14 pounds of boost. Just a regular number, right? We try another number. We say, okay, 22% duty cycle brings us 16 pounds of boost. Well, if we keep filling in this table through every single RPM range and it's perfected to where it is a very flat number every time it runs through the car, the PID never has to activate because the closed loop corrections of PID do not have to activate because it has its range and its deadband. Deadband would be like if a fan turns on for a computer and it doesn't need to turn on every 2 degrees and then turn off again. It's going to have a range in which it's staying off for a period beyond its turn on time and then beyond its turn off time.
I guess other systems call feed forward tables the base duty table, which is
Yeah.
the open loop pulse width control or the open loop values where the target is actually met without needing the PID control. Now, the PID control will help you compensate for the changes in situation, changes in atmospheric pressure, changes in whatever would happen in any kind of circumstance to help it again, reach those targets. Essentially, is that base duty table or the feed forward tables help the ECU put less effort on the PID control, which is what Brian was just discussing. You don't want the whole control to just be PID.
So another really good way of putting it is actually the way this is called is the initial position table. That
Yeah.
makes sense for just about everything. So
That's probably the best name out of it,
that's
all
the
of them.
best name out of all of them.
Yeah.
So initial position. So here's a good one that I was talking about with boost control. This is exactly like I said, 12 PSI. Now we've got 12% duty is getting us 14, 21% is getting 16, 36 getting 18, so on and so forth. Now, this is just a number to look up. Now, these are going to change. We can say due to back pressure here that these might need a higher duty cycle, but this is getting into tuning. This is not what PID is about. Anyways, I'll show you guys while we're here what a PID would look like for this one. So first off, frequency, and then it's got a deadband of 0.3 psi before it even touches anything. So if it's not within that 0.3, it'll enable. If it's within 0.3, it will use that feed forward table, the initial lookup table, exactly as it is.
Is it a plus or minus, or is it a below?
It is a
above?
plus or minus.
So it's basically you're giving it a window of operation above or below target.
Correct. And so we've got on this one.
Now, here's a little question for me. If you're working it that way, what happens when you go beyond target?
Well, that's what I was going to show you. So the reason why I pulled up Mtrons right here is because they do a very good job of when you overshoot, what happens. So it can shut off the controller. So where are you? The one downside is the software is a bit cumbersome. There's a lot going on here. Here's what I was looking for. So on the integral table, we have a port duty in a percentage. Is that right? Upper port boost percent. Yeah. And then we have the boost error, how far away we are from our target. So if we're 5 psi away, it's shutting off the controller. If we're under our target, the controller is on.
One thing to mention, again, our beloved Mtrons. We love Mtron. These things are pretty badass. Not all systems carry all this flexibility. You can come up with tables for absolutely everything, and every axis, every channel in the ECU can be tuned against, which is what Ryan's showing in this particular example. So another thing that we can point out when it comes to strategies with the different brands of ECUs is, even though we're not here to teach you how to navigate the software and where everything is, it's probably on you to click around, see what each table can do. Click in the axis setup, look at what you can do and what's available for a particular table, a particular function. You can find that there are systems that are a little boxed in with features. They're just do this and that's it. And there are other systems which you will find, well, that, hey, I got 4D tuning over here. I can add a math channel, then pull this value over here. You know, a lot of stuff can be done depending on your system. So it always pays to just click around, navigate it. It'll help you get familiar with the system, where the menus are, where the options are, and you won't get any surprises. Or where is this? Or where is that?
There's an incredible video, and actually I think it was a podcast that Nick
they've done a couple. Yeah.
Nick of Mtron did. And he was like, yeah, so we made a 2D, or was it a 1D fuel table? So you have enough information coming in from all these other channels that the fuel table was a single line. It was the funniest thing.
If you ask Ben Strader, this is an inside joke. You'll see the one cell fuel tube.
One cell, yeah.
If you think about it, you can do a one cell tune very perfectly. Having said that, how many other tables are taking care of the rest?
There's a million other tables. So the one thing I wanted to mention was, you really should try to take the whole point of the advanced features part of this fundamentals thing is you really want to take an open approach to all of this. So let's say we want to do injection timing for an engine. Well, the RPM could be a standard axis, but so could injector duty cycle. Think about it. So if your injector duty cycle is, well, obviously you're not going to have the injectors wide open at low RPM. It's based on engine's velocity, right? Well, doesn't that account for more than, you don't need pressure versus RPM. Now you've just made it a single axis of duty cycle. So now
And
you
then
can really start thinking about like, oh, okay, well, what other axes can I use? Effective pedal uh area. You can do oh geez, there's
there's
hundreds
it,
of
it's what I
combinations.
tell it's what I tell people. Computers are logic driven machines. You think about it logically, just like it would, and you can come up with a whole bunch of stuff. One of my favorite things to explain is the 12 position trim knob. Well, while we're in the subject of inputs, you have 12 different positions, and everything can be done with these. You can take the first three and do normal mode, valley mode. You can put one more that's up past that, and you can start doing traction control. A couple past that, you can do boost control. The sky's the limit.
Yeah. So you can have one knob essentially going through and changing all these different modes in the back end because all you're doing is you're taking this input and you're saying, oh, when it 0.3 volt, do this, 0.4 volt, do this, whatever. Another thing that's kind of cool with input stuff is if you have a CAN keypad, you can have one of those keypads change the whole keypad to another whole set of different numbers. So you can have an 8 button keypad that has one key that has 8 different functions on it. And that could pretty much get that keypad, 64 times different keys. Like
Well,
it
if you
just
think
gets
about it,
really weird.
if you think about it, each key, I'm under the impression it's four functions. It's
Eight,
off.
up to eight.
It's one press.
So here, I'll
The
show you.
ones that you have three LEDs, you have one press,
Yeah.
everything's off, or no press, everything's off. One press, first LED. Second press, third press, and then I believe there's also, or is it one, the middle, the third, and then combinations? And how many is that? For Christ's sake!
So
I mean, if you
I
really
brought it
wanted to
up right
get
here.
into it, if
It's
you really
it's
wanted to
just
get
an
into it,
impressive. There is no limitation for the logic. So you've got toggle, which means the thing is just an on-off switch.
there you
You've
go. It's
got
five things.
sequential.
Yeah.
No, but if it's run binary, it's run as eight.
Oh yeah, yeah, yeah. There it is.
And
It's
then
eight
you can also
positions.
have momentary.
Yeah, yeah,
So
yeah.
so you really have 5 different functions for each of those keys. And then
Unreal.
it's just so what it is, the reason why it becomes eight is they have different LED that can overlap, so you know which one's
Yeah.
which.
And that's an
Um,
8 position switch right there.
yep, right here.
Yeah. No, I mean you
So
can, instead of the rotary knob, you can just use the 8 positions on the
yeah,
on one button.
yep.
Yeah,
So
so that's 8 by 8. That's 64.
and here's like a perfect example is a boost clamp table. Um, I like thinking as a driver, I would like to use knobs more than I would switches for certain
Yeah,
things, right? But
especially
the
if you're wearing big, thick gloves.
yeah, it just depends. So like for traction control and let's say torque modeling, which this is not for this video, I would use a knob. And then for something like a rolling anti-lag, I would use a momentary button on a keypad because that you just let go and you go. So anyways, let's jump back into our little subject here. We
Yeah,
had a bunch of
roll
cool
back.
stuff. Yeah, we went deep. We went hard in the paint on that one.
Well, I mean,
Uh
so pretty much every system or every function that you get with the ECU is some sort of closed loop when done properly. Again, depending on your ECU's vast or simple capabilities, you will have more open loop than closed loop stuff. You know how basically you just take a table, run a duty, and that's it. Just whatever duty, that's what comes out. But a lot of the systems nowadays will have cam control, boost control, O2 control, basically the drive-by-wire, all that stuff. Everything is closed loop.
so this is one of the boost PIDs that I use pretty commonly. This is when we have our error, the boost controller is pretty much shut off. So 1 psi of error, don't do anything. Close enough, use open loop table off of what we had calibrated in our initial lookup position table. And then when we are far away, that's when you're activating. And then this is just an arbitrary speed, and these are really not identical from ECU to ECU. So play with it, you'll
And
figure out what
and from
works.
and from device to device, each thing, each
Yeah.
hardware requires different control. It's the same with injectors. Each injector is different. Each coil is different. So each device, each feature will require attention to the PID that it requires.
So as a good rule of thumb that I've used so far for in this scenario of boost control, my P is about 15 to 20% higher than my I, and I'm not using derivative. So
Say that
that's
again.
for this. So my P is 15 to 20% higher than my I value,
Mm-hmm.
and my derivative is zero for a
But
three-port max solenoid, which has a completely different dead time than a four-port max solenoid. Flows a lot more, and it's a
yeah,
lot more erratic.
yeah.
Speaking of erratic, the three-port max solenoid, hot day, cold day, different boost offsets. Normally, when characterized, it can be about a PSI and a half of little oscillation of just normal stuff. You could try to characterize it perfectly for every air temperature, but that does not account for heat soak for most models. On a four-port max solenoid, and why I don't have one for my car, I actually have two three-ports. Um, that's going to have almost a 3 to 4 PSI offset of consistency. It can have the exact same open loop, be perfectly characterized, and you're still having a little bit of differences between air temperature, air density from elevation. It's just not able to maintain a perfect control as best as you can optimize it for most ECUs.
And I would also probably add to that the characteristics of the inner workings of the Mac valves. If you get a slightly different part number, you get a slightly different wattage and I think coil spring pressure internally. Obviously, we try to supply the same one all the time so we don't have to deal with that sort of thing. And but you do see when people buy the cheap ones that they think they're getting a legit one and it actually isn't, even though it looks identical, has a label, comes in a box that looks exactly the same. When you hook it up and you test it, you find that it doesn't react, not even close to what you were expecting. So get your good quality stuff from a known supplier.
Funny enough, we're talking about higher end ECU stuff.
Mm-hmm.
Entron has an entire solenoid dead time, just like an injector dead time for
That
a
is
three port,
awesome.
for a three-port max solenoid. Boom, right there.
That is awesome.
So with voltage, like I'm saying, we're getting this dead time characterization for certain things. Um, then there's going to be these compensation tables. So like air temperature, exhaust pressure, all this stuff. As much as you can bake into the back end to calculate for you and actually get you close, and then you can identify what your needs are, the better the vehicle is going to run day in, day out. But
One thing to note is obviously you need to start with a rock solid, let's call it open loop foundation. Because if you start trying to get many corrections stacked up on each other, but your closed loop is not correct, or your initial open loop duty values are not correct, or your feed forward tables are not correct, it's just gonna cause a nightmare and run horrible.
but at the end of the day, tuning has nothing to do with any of this. And we're going to go through a whole series about what actual engine tuning is. Um, this is like software manipulation. This is like we're we're buttering the bread, but we got a whole sandwich factory. Like it's a different situation. Like an engine is an air pump. Like this, we're just manipulating some software to idealize what we can, but that's not actually how an engine operates. And we can go through that with really good examples are like acceleration enrichment, how I go over throttle body sort of stuff, um, how different, uh, I guess, velocities will change torque output. And we're really modeling the airflow of the engine and focusing on how to optimize the torque output. So
Well, I mean, that is a whole
that's a big,
discussion. That is
big.
a whole discussion in itself. Heck, intake manifolds and all the components that are related to it is a whole subject in itself. You
You
have
have You have the
Long manifolds, short manifolds, big throttle body, small throttle body, venturi, no venturi,
we
individual throttle bodies.
the whole thing with a plenum is you're actually supposed to be creating a wave pattern that's a constructive wave pattern from the way that it's bouncing back off of the last pulse. And so it's actually pulling even more vacuum when it's a properly tuned intake manifold. It's a very, very unique thing. Honda does a great job at this. Actually, the REW intake manifold is a really good job of this. That's why the plenum's located where it's at. That's why
That's
there's
why the
certain
shape it
baffles
is,
that, yeah, the internal baffles of exactly how they are. If
the
people are like,
length they
oh,
are.
the diameter the piping is, it's all a tuned intake manifold. So when everyone goes in there, like, I'm gonna hog this out, I'm gonna do this. Well, you just lost all this mid-range, and you may gain similar to what has been seen on a, let's say, popular upper intake manifold option on the market currently. And yes, you are going to gain top end, but at the expense of 4 or 5 thousand worth of good RPM, better torque down low. So,
Well, the I guess it all harkens back to our initial overview talk where you say, what do you want to perform in? What do you want the engine to do? Do you want a broad power band? A broad power band comes at the cost of high RPMs. Upper torque, you want upper torque. Okay, so what's happening down low? You're going to lose all that. Okay. Do you want a fast revving engine, a slow revving engine? Do you have, you know,
well, we can
turbo,
say,
NA, nitrous,
yeah,
whatever?
we can say different strokes for different folks, right?
There you go.
When you understand your needs and your wants, then we can help guide you there.
What you talking about, Willis? I had to do
Got to do it.
it.
So my whole thing is I always ask a bunch of questions to my clients. I'm like, what are you trying to do? Where do you drive? Oh, you're at 11,000 feet? Okay, your turbo's too big. And then we go
No.
from there.
Oh, you're in Colorado. Oh, okay, great. Oh, you're in Quito in Ecuador. Oh, great. Oh, you're in Lima, Peru, sea level. Okay, great. Your gas octane quality is piss. Okay, all that stuff has to go into account.
You're
Um,
surrounded by 5 E85 stations and you run on pump gas?
oh
That's
boy.
just not smart.
You want to talk a little bit about specifics of closed loop in any specific function
Not
or feature? No.
not really. I think we handled that pretty well. Do you have something else in mind?
Well, to be honest, since our section initially started at life as inputs and outputs, there is no amount of inputs that is too much. Of course, you're limited by what your ECU can do, but the more data you can gather, the better. So, oil pressure, fuel pressure, temperatures before and after the intercooler, temperature at the manifold itself. You're worried about heat soak, but then again, heat soak is probably an illusion. Um, what is your EGT? What is your exhaust back pressure compared to your intake pressure? Is your intercooler actually restricted? You can measure map pressures before and after the intercooler. You can't have too much data. More data gives you a lot more info to dial the engine a lot better.
Yeah, I would say that when you have all these sensors working as they're intended, it gets you to where you're saying, oh, well, my EGTs spike up at this position, and I have a boost pressure loss at this position. I have a wastegate opening up, or I have back pressure that's creating this problem for my setup. This should be a good stopping point. Um, there are certain things that I actually had Josh write to me. It was amazing. Um, Additional sensor selection and how to leverage them in regards to turbo speed, EMAP, EGT, multiple IMAP sensors, so on and so forth. Those additional sensors are going to give us an idea of the vehicle's limitation and where a safe, good stopping point is. We can push all the power we want. We can throw 38 pounds of boost at a journal bearing turbo and the engine's screaming for life, but it's not doing its thing. Or we could say, hey, our back pressure is 60 psi and we're aiming for 30. I don't want a 2-to-1 ratio. We're going to stop closer to 1.7 to 1. We can do all these different things to really make sure this is going to make a lasting setup. Because a
Yeah.
lot of people can tune a car, make a bunch of power, and then it's like, oh, there goes next week, and then it's back in the shop again, and oh well.
Yeah, I mean, sensors can give you a good idea of component capability, like I just mentioned earlier. I mean, if you're monitoring intercooler temperatures both pre and post, and you're not really seeing an improvement past the intercooler, or some people have seen they put map sensors after the turbo and at the charge pipe before the throttle body, and you're seeing an increase in pressure before the intercooler. That means your intercooler doesn't flow enough. So all that can account for valuable data that can help you make better decisions, make more power, have more fun, and just go faster.
A
I think we're
really
done,
simple
right?
one that I always love to look at is a natural aspiration motor with a map sensor, wide open throttle. We're watching the map sensor fall and fall and fall and fall with more RPM. Well, the
Mhm.
very simple thing of that is it's running out of air. It's got a restriction or something is unhappy in which the channel of air going to the engine is not optimized. So
It's a restriction, pure and simple.
yeah,
Whether it's too big of a throttle, too small of a throttle, too big intake ports, too large intake ports, too small intake valves, too large intake exhaust valves, too large a header, too small a header. You never know until you check everything.
those small pod filters that people are like, yeah, I've protected my turbo, except for that thing's rated. If you go to knn.com, it's like, here's a 400 horsepower filter. And it's like, the guy just put it on an 800 horsepower car. And he's wondering why he loses 70 horsepower when he throws it on.
I wish more people had more access to a flow machine, at least just to see their component be tested and showing them exactly what they bought. It says, hey, okay, we're flowing, let's say 100 cubic feet per minute. You put the flow filter on there and it drops to 45. Okay. Yeah, data,
Data is
important.
important.
So our next section is going to be data logging.
That'll be fun. You guys will like it.
Yeah.
All right.
See you there.
Catch you guys in the next one.